In this video, we're going to take a look at the standard enthalpy change of combustion and how we can use this value to determine the enthalpy change for any reaction. So we need to start with our definition of what standard enthalpy change of combustion is. So it's given the symbol delta H with our circle with our line through it to tell us we're at standard conditions with a lower or subscript C. So that tells us that this is the standard enthalpy change of combustion. Its definition is kind of wordy, but let's work through it. So it's the enthalpy change when 1 mole of a substance in its normal state is completely burned in oxygen to form products in their normal states under standard conditions of temperature and pressure. So essentially what this definition is saying is if we have a reactant that we are combusting, so is undergoing combustion, then we're balancing that reaction for 1 mole of the thing that's undergoing combustion. So for example, if we have methane gas and we react that with oxygen, then we produce its normal products, which is CO2 gas and water. And then what we would do is we would balance this for 1 mole of our methane gas. So if we were to balance this, we'd have a 2 here and a 2 here. Now we're balancing based on 1 mole of our reactant. So similar to enthalpy changes of formation, you may need to use fractions here, here, or here, and that's okay because this is the definition for the enthalpy change of combustion. Another thing to note, the enthalpy change of combustion for oxygen in its standard state gas is 0. And that's because the definition says if we take our reactant, so in this case, if our reactant was oxygen, and we reacted it with oxygen, essentially there's no reaction here, right? Because it's all just oxygen. So that means the delta H of combustion for oxygen in its standard state is 0. Now we can use enthalpy changes of combustion to figure out the enthalpy change for any reaction. And it looks very similar to the enthalpy changes of formation and how to figure out an enthalpy change of reaction, but slightly different because if we take a look and we use Hess's law here, and we're looking at any reaction going reactants to products, so this would be our enthalpy change of our reaction, then we would have enthalpy changes of combustion of our reactants going to the products of combustion, and then we would have our products going to products of combustion. So looking at the indirect route here, we would take all of the enthalpy changes of combustion of our reactants, and we would need to subtract all the enthalpy change of combustion of our products. So we are adding the enthalpy change of combustion of our reactants, and we are subtracting the enthalpy change of combustion of our products. And of course, if there's any coefficients, we still need to include those in our calculation as well. So we can summarize it in this equation here, where we have the enthalpy change of any reaction is equal to the sum of the enthalpy change of combustion of all the reactants minus the sum of all the enthalpy change of combustion of the products. So it's a nice way that we can use enthalpy changes of combustion to figure out the enthalpy change for any particular reaction. Let's look at an example then. So we want to figure out the enthalpy change for the following reaction using standard enthalpy changes of combustion. So let's set up our equation first. Our enthalpy change of our reaction is going to be the sum of all the enthalpy changes of combustion of our reactants minus the sum of all the enthalpy changes of combustion of our products. So expanding that out a little bit further, we have 6 carbon graphite, so we would have 6 times the enthalpy change of combustion of carbon. We have 6 H2s, so we'd add 6 enthalpy change of combustion for our H2s. We have 3 O2s. I'm going to throw it in. We know that the enthalpy change of combustion of O2 is 0, but it's good practice to include it here. And then we're going to subtract our products. So we only have one of those. So we just have the enthalpy change of combustion of glucose. Okay. Now, there are lots of data tables available for you to look up these values. There is a data table in the data booklet that you can use. So I've pulled the values from there. So for carbon, it's negative 394. For hydrogen, it's negative 286. Now remembering oxygen 0. And then for glucose, it's negative 2803. Okay, and if we do this calculation, we come out with negative 1,277 kilojoules per mole. So the delta H of reaction for this reaction up here using the enthalpy changes of combustion is negative 1277 kilojoules per mole. So that's it for this video. We'll see you in the next one.